Hello and welcome back to Calculus. This is for section 3.7 in the OpenStax book of Calculus, volume 1. I am going to organize my materials slightly in a different way. I will be very brief when I talk about section 3.7. This is on the derivatives of inverse functions. And the reason I am going to do a very light treatment of this section is because a lot more things will make sense after we study section 3.8, the section on implicit differentiation. So a lot of things that you find in the book under section 3.7 will be covered in my video lecture for section 3.8. Okay, so I hope you understand that. And so here is a very brief presentation of section 3.7. All right, so the question here is, what is the derivative of the inverse of f? Okay, and I have, because this content heavily depends on the picture, I have drawn this picture rather carefully. You have this function f, which is this function that's going up to infinity, sort of like the exponential function. And then the inverse is like the log function. It grows, but very, very slightly. Remember that the function and its inverse, the graphs of the function and its inverse are sort of, well, not sort of, symmetric to each other with respect to this line, the 45-degree line, y is equal to x. And that's because, you know, you're switching x and y, and when you switch x and y on the plane, they will give you points symmetric with respect to this line. All right, so the question is this. Now, as I said before in the introduction, much of the contents you see in the book under section 3.7 would make a lot better sense after you study implicit differentiation in the 8th section. So I am going to leave a lot of content out of 3.7, but don't worry, I will cover everything you need to know under 3.8. All right, now just to review the idea of inverse, you know, you have the set A, the domain, set B, the range. And if you have a function f, that would send, let's say, I think, yeah, okay, so x to y, right? Then f inverse is actually going to send us back this way. And this only happens if f is 1 to 1. If f is not 1 to 1, you cannot define the inverse function. This was back in chapter 1. Okay, so when f is 1 to 1, the inverse, f inverse can be defined, and it'll throw or map y back to x. Right, so now we know, for instance, f inverse followed by f will take x to x. Okay, so this is the identity function on, we say this is the identity function because it doesn't do anything. You know, it's going to send x back to x. So it's identity function on A. Right? Now, if you do the other way, f of f inverse, so you do the f inverse first and compose it with f, then of course the original input has to start at B, and so y gets sent to y, and this is the identity on the set B. Okay. And by the way, these are used as the definition for the inverse functions. Okay, so with that, let's keep these in mind. And now what I'm going to do is to try to define the inverse, the f inverse, trying to define the derivative of f inverse at this particular point A, right? So what I am after is this. That's the question that I am going to focus on, all right? So how do you do that? Well, the picture here is this. You have, well, by the way, I am calling this, okay, so you can see here, f inverse of A is equal to this value here, okay, this point here, but the opposite one here is BA, right? So this point is B, and this point is A. And so in this picture, what we have is this. F sends B to A, and F inverse sends A to B. Okay, and that's why, I mean, at least that's how, the way I set this up. Okay, so this point here is BA, and this point here is AB, except I'm writing this as A, comma, the inverse of F evaluated at A, which of course is B. All right, So if you look at this picture, you can see the symmetry, all right? And what we have is this triangle here. Let me color this, shade this. This triangle here is exactly the same, or in geometry, you say congruent to this angle here. They are flipped, okay, with respect to the line y is equal to x. And so the slope of this triangle is, of course, q over p. And this is actually sort of like, swapped, the flipped and turned by 90 degrees, right? Let's see, negative 90 degrees. Yeah, degrees over here like this. And so the slope of this is the inverse or the reciprocal of this. So let's try to remember that. F inverse, sorry, the derivative of f. The derivative is the slope of this tangent line here. You see that? The derivative of that tangent line at point B is equal to, from this picture, it's Q over P, right? And the inverse function, F prime, the derivative of, the inverse function is the F with a -1 as a superscript, but the derivative of the inverse evaluated at A is the slope of this tangent line, and that is rise over run, P over Q. And what's important to note here is that these are reciprocals of each other, inverses of each other, right? The product is equal to 1. Right? And so that's really all we need for this one. The derivative of the inverse evaluated at A is 1 over the derivative of F evaluated at B, okay? Which is to say that this is the derivative, 1 over the reciprocal of the derivative of F evaluated at B. But remember, B is just the inverse. The B is the value of the inverse evaluated at A, because remember, F sends B to A and F inverse sends A to B. So this is actually the same as, B. And that is pretty much all we say in this section. This is the main result of this section, section 3.7. And I should call this the inverse function theorem. It sounds really, fancy, but it's okay. It's as far as the importance of theorems is concerned, this is not one of the most important theorems or anything like that. The chain rule is far, far more important and useful, right? So again, let's write this down. The derivative of the inverse of F evaluated at A is the reciprocal of the derivative of the original function F evaluated at what is called the inverse image of A, or the inverse of the function F evaluated at X, all right, at A. Now, typically, we don't pick the point A, right? So for the expression or for the statement of the theorem, we just use X, and this is pretty much it, okay? So that's called the inverse function theorem. Just remember that we have studied this, and I will do one example, but not much more. Again, because there's so much more you can do once you study implicit differentiation in the next section. All right, let's do this one example. Let's differentiate this function. Okay, differentiate g of x, which is the cube root of x. What is that function? It's x to the 1/3, right? Using the inverse function theorem. Hope you can see that I have abbreviated all of these words, like the inverse function theorem. I like to use abbreviations so I don't have to spell the entire words. All right, so that's that. Okay, but you realize G is the inverse of what? If G is the cube root function, that is the inverse of the cube function, right? I mean, taking the cube root is exactly the opposite of taking a number x and cube it. So Think of g as the inverse function of f, where f of x is x cubed. So just by looking at this, the g prime of x by the inverse function theorem is the derivative of the inverse of f, which according to this is 1 over the derivative of this evaluated at this. Now that's really confusing, isn't it? Okay, so what is that? Well, think of the derivative of f. That's 3x squared. So here I write 3 something squared, right? But see, the derivative of f at x is 3x squared. But what this is saying is I have to write the derivative of f evaluated at the inverse image of f. So what is that? This is the same as g of x, right? The inverse of f inverse of x is the same thing as g of x, which is x to the 1/3. So the answer is going to be 1 over 3 times x to the 2/3. Or you can write this as 1/3 times x to the 2/3. Now, if you stop and reflect on this, this was the function I was differentiating. And what we have is that this exponent came to the front. Does it remind you of something? It should, okay? That's exactly what we did with the very first power rule we learned, right? So 1/3 becomes the front as the coefficient, and the new exponent is exactly 1 less than 1/3. Oh, sorry. I should have put minus here, right? Because this happens in the denominator. So the power rule still works. You take this exponent, put it in the front as a coefficient, and subtract 1 from it to create this new exponent. And so it seems like the power rule still works, okay? And we will verify that, and we'll restate that in the next section. As for this inverse function theorem, this is one application of it. And it is confusing, right? Because we are talking about like taking the derivative of f and evaluating it at this f inverse of x. The good news is you don't really have to do this, okay? Because again, once you study section 3.8, the technique called implicit differentiation, right? This will become obvious, right? So that's all I'm going to say about section 3.7. I'm not saying section 3.7 is irrelevant or not important or should be discarded, but pretty much everything you are going to learn in this section can be covered in the next section. The only thing that you will not see in section 8 is this theorem, the explicit statement of this theorem. And it could be useful, especially if you remember this came from this geometry of the the right triangle and its counterpart, with respect to the symmetric triangles with respect to the line y is equal to x. So that could be useful in the future. And that's about it. Okay, so that's it for section 3.7. Next time we'll study implicit differentiation.